As progress in rocket flight continues, missiles capable of greater speeds, accelerations, and distances are being developed. With progress, accompanying and often created by the improvements themselves, have come problems of considerable magnitude. Areas of material, construction, and instrumentation have become greatly complicated. Some method of pre-testing components was needed. Another alternative might be found in laboratory methods. Components might be subjected to conditions similar to those encountered in actual flight. However, the nature of these flight conditions was unknown. Track-borne rocket sleds. They are capable of high accelerations and velocities, and under controlled track conditions, these can be very accurately measured. As a test bed, their easy recoverability and reuse recommend them. Here might be one possibility.
There was an earlier track that was quite useful in the early development of Sidewinder, but its capability was limited. It was from that experience that the need was foreseen for a longer and more capable, higher velocity track.
And now, Sonic Boom Railway. It may not have come up with the concept, but China Lake was a pioneer in the development and operation of high-speed and specialized tracks. To bridge the gap between the wind tunnel and the free flight regime, in the service of pure research, proof of concept and developmental testing, captive flight, terminal ballistics, weapon systems, and aircraft systems, bits and pieces. Damn near everything imaginable has been flown down a track. In support of the China Lake RDT&E program, in support of the fleet. Flying along the ground at high speed, let alone at multiple Mach, presents unique challenges. Weight and balance and aerodynamic profiles get tricky quick. Just keeping things on the track for the duration of a test can be difficult. But these cutting-edge outdoor laboratories became essential. In the years before the supercomputer, only so much could be done with a slide rule. And even today, with even the most cogent of models, simulation can't substitute for everything. Beginning in 1946 with the little 1,500-foot terminal ballistics track, China Lakers pioneered track testing in support of weapon and aircraft development, along with the design and equipping of the test tracks themselves. The station's early efforts ranged from defining the theoretical limits of wheeled sleds to creating sophisticated instrumentation for the test items, the vehicles, and the tracks themselves, and to figuring out how to stop the things once they got going. The station also began high-speed track operations in 1946 on its nearly 3-mile-long transonic track, which saw some spectacular test series. And was an essential asset for the development of Sidewinder. Several tracked ramps, too, were designed for test launches of missiles and rockets, and to simulate an aircraft in flight. The 450-foot Lark ramp was opened in 1946 and demonstrated for a very VIP audience. 550-foot 6-degree ramp replaced Lark in 1951 with a more versatile facility. The fuse range at Randsburg Wash maintained ramp launchers as well. The Crosswind firing track, opened in 1951, provided the only ship-in-motion simulation for missile launching. And in '54, the terminal and exterior ballistics track added another unique capability: a supersonic track that allowed open-ended firings over an instrumented range. While the early tracks were proving their worth, and their deficiencies as weapon systems became ever larger, faster, and more complex, the station was creating its next-generation track, the biggest one, the fastest one, the archetype, the Supersonic Naval Ordnance Research Track, SNORT. Proposed as a 10-mile triple-rail modern monster, SNORT opened in 1953 on a bit more practical but nonetheless impressive scale. 4.1 miles long, heavy carriage dual rails, target towers, water brake, highly instrumented, highly flexible. The tracks quickly proved to be an amazingly versatile venue for highly controlled testing in a dynamic environment. Whether to simulate free flight or to initiate it. And it's a lot cheaper to mount, say, a fuse, or just a tail, or a fin, or a dome, on a small sled and run it down the track, than to build and fire actual test missiles, or even just carry them around, over and over, past cameras and sensors, through rain, or birds. On the China Lake tracks, fuses, sensors, target detecting devices of all sorts fly at real speeds past real targets. And test items can be flown over and over, or let go, with the sled pretending to be an airplane firing rockets from prototype launchers, automatically releasing bombs over target, firing missiles from internal bay or wingtip rail, firing live weapons when need be, at better than Mach 5 when need be. And over the Cold War decades, the China Lake tracks were used for every odd thing, ranging from gently catching atomic artillery shells in flight, testing critical components of the new generation of continental defense, assuring the stability of secret nuclear depth bombs, to smashing strategic missile motors into immovable objects to find out what might happen in an accident. The tracks have been used to evaluate propulsion systems and components, firing forward, backward, and sidewise. And to analyze unique warhead dynamics, from the patterns of the blast to the penetration possibilities of the dumbest bombs and the smartest missiles. Blasting through track terminus targets at oblique angles, armored hulls, and yards-thick bunker walls. Or to watch a warhead function from otherwise impossible angles. Complete airframes and small parts thereof, of not only missiles and rockets, but of aircraft of all sorts, of drones of all sizes, and even of manned spacecraft flew down the tracks. Evaluating aerodynamics, structural integrity, blast damage in flight. It's a lot safer for our pilots, too, to test new ejection seats and parachutes by running instrumented dummies down the track. Especially when something goes wrong. That's probably what the tracks are best known for, helping to ensure our aircrew's avenue of escape, Although the popular imagination, where rocket men routinely rode the rocket sleds, was never the case at China Lake. The unique instrumentation of the track complex has also supported static-tested oddities, ranging from barriers to keep our embassies safe from rocket trucks, to amazing upside-down ejections from full-scale aircraft cockpits. The Navy has loaned out the China Lake tracks to other activities over the years, too, to other services, and to industry. And sometimes, even more dangerous things have ridden the China Lake rails to help pry out their secrets or to spar with fleet defenses. And after 5.5 decades, SNORT remains the archetype and retains the dual-rail speed record. There are newer, higher-tech, far more expensive tracks, but nothing that'll do what SNORT can do. Fire huge, heavy carriages at high speed, lob live ordnance at the same range, and launch high-risk payloads that other activities don't dare run down their pristine rails. And at the same time maintaining the in-house ability that allows the track to be resurrected from ruin and readied in short order for yet another run, bridging the gap for a new generation of breakthroughs. But that's another story.
Placed in 1947 by the Aviation Ordnance Department of the Naval Ordnance Test Station in U.S.Navy, this 1-mile outdoor railroad track immediately proved a convenient instrument for supplying moving targets in the development program for aircraft fire control systems. Gasoline rail cars with speeds up to 60 miles per hour were the first targets and adequately simulated wind and evasive action. Their success indicated the need for faster vehicles. Rocket-powered cars riding on flanged wheels were the next step toward bringing target speeds up to simulated air-to-air velocities. The nominal success of these 120 miles per hour vehicles indicated the feasibility of attaining even greater speeds, provided the limitations of rotating wheels could be overcome. Magnesium skids proved to be the answer, and with their advent, a successful run of supersonic speeds were possible. Facility located on Baker 4 Aircraft Range at Inyokern is a standard gauge railroad track laid to the best commercial tolerances. The initial track was 5,280 feet long. Standard ties and 75-pound rail are laid on the usual gravel ballast. Because the initial rocket motor blast tended to remove the ballast around the breech end of the track, a concrete apron was installed for the first 200 feet. At the same time, special anchors or tie plates were designed to make alignment of the first section of track simpler and more accurate. The first firings were from east to west, but in 1949 the program necessitated firing from the west end of the track, and this 500-foot extension was added. The rails were placed on concrete piers to raise the roadbed above the ground to minimize blast effects. Magnetic pickups installed for the full length of the track have been the basic instrumentation for determining position, velocity, and acceleration. Pickups are spaced 100 feet apart except for the first and last 1,000 feet, where the interval is 25 feet in order to get more detailed data relative to acceleration and deceleration. A magnet carried on the axle of the car induces a current in the pickup coils as it passes over them. Pulses so generated are recorded on a recording oscillograph along with a 1,000 cycle per second time base to give accurate position, velocity, and acceleration measurements. When more detailed data over limited sections of the car's travel is required, the bow and acceleration camera augments the magnetic pickups. High-speed cameras are also used for checking performance of specific components. Automatic 16mm cameras are frequently carried on the cars to record the performance of various accessories and instruments. With the development of vehicles to the point where captive pre-flight testing of missiles was possible, a trailing wire system for transmitting data from the moving car was developed. This was designed to check radio telemetering during acceleration by direct wire transmission of duplicate data. Stopping vehicles, always a problem at speeds of 500 feet per second or higher, has been given careful attention. Most of the early cars were stopped by forward-firing retro rockets. These rockets, usually smaller than the power rockets, were mounted on the forward end of the vehicle. Depending on weight and speed, 1 or 2 rockets were used. More control of deceleration led to considerable experimentation with various arresting systems. The use of increased frontal area was one of the earliest methods tried. First used in conjunction with retro rockets, it was later used without them. This system was highly successful with comparatively slow and heavy cars, but could not be used where maximum speed and acceleration were required. An arresting system of dragging chains and cables picked up by the car was only nominally successful. The use of controlled depth which intercepts a scoop or vein on the car has proven highly successful. The sand is placed between the rails and its depth carefully gauged. The scoop or vein is attached directly to the car. When the scoop comes into contact with the sand, the energy imparted to the sand through the scoop acts as a brake. The controlled depth decelerates the car at a predetermined rate. Both slow and extremely high-speed cars can be controlled by this system. Several different configurations of scoops have been tried successfully. The advent of controlled deceleration has greatly increased the usefulness of the entire system. When early tests indicated that the maximum speed practicable with wheeled vehicles was in the order of 120 miles per hour, the development of cars riding on magnesium skids was started. The early cars were skeletal frames with the rocket motor bodies generally acting as the main longitudinal structural member. Cars weighed in the order of 400 pounds. Speeds were immediately increased to around 600 miles per hour or over 850 feet per second. The success in using standard railroad track for velocities beyond the sonic barrier indicated that such vehicles were practical for other uses. Pre-flight testing of captive missiles, variable attitude firing of guns, rockets or guided missiles, and the carrying of airfoils to test blast effects and damage by projectiles suggested themselves. One of the first experiments in the expanded program was this car, powered by 2 Model 38 rocket motors which carried an airfoil. A .50 caliber bullet was suspended over the track in a position to intercept the airfoil. The successful runs with light cars at velocities as high as 1,400 feet per second led to the development of vehicles to carry greater loads. The final tests of this series were made with this carriage carrying a mock-up that approximated the weight and balance of the Lark aircraft. The tests indicated that by controlling the temperature of the motors, the velocity could be controlled to around 500 feet per second and the acceleration to around 18 G as specified. The increased frontal areas eliminated the necessity for retro rockets and limited deceleration to less than 4 G as required. The value of this facility has been well proven, and development of further uses continues. One of the newer developments is this carriage for the controlled launching of rockets at simulated aircraft speeds. This car is carrying two 5-inch rockets with special deflectors to control the trajectory in a longitudinal plane. The value of being able to fire such missiles at accurately specified points along the track with the consequent possibility of concentrating instrumentation in relatively close proximity to the release point is proving most useful in gathering data of a high order of accuracy. For the first time, mocked-up sections of an aircraft's fuselage with multiple rocket tubes firing at exactly predetermined positions and under controlled conditions is possible. The successful development of additional vehicles for special purposes promises to make the facility a most versatile instrument for the scientist and engineer in the search for highly accurate data in the fields of ordnance, ballistics, and aerodynamic research.
Attention all personnel, stand by for a 1-minute firing. Mark, 60 seconds to firing. 50 seconds. 40 seconds. 30 seconds to firing. 20 seconds. Roger. Roger. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Mark.
For nearly 2 years before SNORT reached the design stage, historical surveys of existing tracks were being conducted at both Edwards Air Force Base, California, and at Holloman Air Force Base in New Mexico. It was evident from these investigations that the precision alignment requirements for SNORT were far greater than those ever built into any other standard construction, and therefore could only be resolved in the actual SNORT installation. The track is 2-rail standard gauge railroads supported by a continuous reinforced concrete beam. It is straight in plan, bearing approximately north 3 degrees west. The grade line is approximately minus 0.5%, having 3 vertical curves, all parabolic and tangent to grade. The end of the track, 4 1/10 miles away, is nearly 106 feet lower than the launching end. Beginning construction, the Coast Geodetic Survey located monuments at 2,000-foot intervals on a line 300 feet west of the track's center line. Additional monuments, located by the architect-engineer, was set parallel to and 60 feet west of the track center line at 500-foot intervals, identified as track reference or TR monuments. There are some 695 tons of various sized reinforcing steel in the track beam, accurately spaced and firmly tied to conform to the rigid tolerances demanded by the specifications. Concrete was batched at a well-organized plant situated about 5 miles from the track site. The mixed design amounted to 3,000 pounds per square inch. (13,900 cubic yards of concrete were poured in the track beam and underpass within the tolerances of 0 to minus 1/4 inch of the theoretical grade line. The beam was poured in 2 lifts with an average of 600 feet per lift per day. The rail groove at the top of the beam was finished by hand, which materially assisted in meeting the final track specifications. The beams were stripped after 72 hours and the forms were reused. Excess concrete was chipped away from the sleepers. Damaged anchor bolts were rethreaded. This sketch shows the overall dimensions of the beam section together with the earthwork performed. 36,700 cubic yards of excavation involved a total of 68,000 cubic yards of fill, compaction, and grading. A minimum of subgrade, compacted to 95% proctor, comprises the cut and fill areas, plus an additional maximum of 3 feet of subgrade compacted to 90% proctor in the fill. The rail sleeper unit was constructed so as to permit independent vertical and horizontal adjustments to the rail. There were 530 tons of sleeper units installed in the track beam, each weighing 77 pounds. Complete sleeper assemblies were installed at 50-inch centers, allowing for future aligning refinements. The installation of the sleepers were kept within a horizontal tolerance of plus or minus 1/8 inch and a vertical tolerance of 0 to minus 1/8 inch from the theoretical grade line. A standard transit was used to perform the preliminary alignment relating to the horizontal control of the sleepers. The rail sections are standard crane rail weighing 171 pounds per yard. They are 50 feet in length, having a tolerance of 0 to plus 1/4 inch at 70 degrees Fahrenheit. Rail ends were milled square to a tolerance of 4/1000 of an inch with reference to a theoretical railhead center line. In order to produce continuity of alignment, steel dowels 6 inches long by 1 inch were used in all joints. Rails were placed upon the track beam by means of specially developed tools. After careful placement on the sleepers, they were jacked into place, meanwhile maintaining a rail temperature below 70 degrees Fahrenheit. Impact wrenches were used for the initial tightening of all rail anchors. The problem of aligning the rail to tolerances of plus or minus 3/1000 of a foot vertically and 5/1000 of a foot horizontally from a theoretical grade and center line at any point throughout the entire length of the track was a challenge. Furthermore, there was no assurance that once aligned, the rails would remain within the limits specified. An optical method, utilizing a telescopic jig fixed over a brass top or F monument located 6 7/8 inches west of the center line of the west rail, and a fixed target over the adjacent F monument, together with the use of a sliding target, adjusted the west rail grade and center lines. The method was tedious and exacting. Sight distances were limited to 50 feet. Surveys were necessarily run at night when temperatures dipped below 70 degrees Fahrenheit. In order to obtain the tolerances, the contractor surveyed the alignment 5 times. Any increase in temperature above 70 degrees caused the track to misalign. However, at lower temperatures, the rails returned to their original positions. The east rail was aligned in daytime by gauging from the west rail. A check survey of the optical alignment was run utilizing the stretched filament method, whereby a monofilament of nylon is accurately supported and referenced from the F monuments along the track beam. The rails can be checked in one operation, both horizontally and vertically, at any time during the day. Temperature has no effect on the accuracy of this method and is twice as fast. Another instrument used for aligning the rail where additional sleepers are required is this aluminum I-beam and dial indicator. Upon approval of alignment, sand is blown from the trough beneath the rails. The hot asphaltic grout used to dampen any resonant harmonics set up in the rails is poured in repeated applications to attain a 3/4 inch thickness. This 3-story reinforced concrete structure is the test control building. It provides space for instrumentation, plotting, test coordinating, photographic processing, offices, telephone and mess facilities, an observation tower, and an electronic maintenance laboratory. The windows in the observation tower are composed of 2-inch bullet-resisting plate glass. The solid fuel storage building is igloo type. It is reinforced concrete also and covered with 2 feet of earth over its entire outer surface. In addition, this 25 by 40-foot building is further isolated with reinforced concrete barricades. 3 test assembly rooms are housed in this building. The blockhouse, 2/3 below the ground, has concrete walls 3 feet thick. Steel plates protect 2 of the walls above ground from rocket blast, while 1 foot, 4 inches of reinforced concrete provides overhead safety. Instrumentation wiring is carried through an 84-inch tunnel from the firing blockhouse to the launching area. The scope of the electrical systems consists of 13 miles of pole line to supply 34,500-volt power. Telephone and fire alarm systems, together with 87 substations, 8.5 miles of 5,000-volt primary circuits, 16 miles of conduit, and 1.5 million feet of 2-conductor signal cable, plus camera stations and outlet boxes located parallel to and east of the track. Magnetic pickup boxes were placed in the track beam at 50-foot intervals to facilitate timing. The starting area is bordered by an earth and concrete barrier 450 feet long, partially surrounding the concrete slab, with 6 transfer rails, 3 fireproof vaults, decontamination showers, and an armor plate barricade. A well was drilled near the end of the track and a pump installed capable of producing 250 gallons of water per minute. The water is pumped directly into a 550,000-gallon open reservoir. Then, at a rate of 1,500 gallons per minute, it is pumped through a 14-inch pipe running parallel to the track, down into the 10 inlets in the beam trough. The trough contains Marsden matting or pierce plank, together with adjustable weirs and dams which control the flow of water. The water drains out of the track beam into the reservoir for recirculation as required. thus forming the water brake system. Scale models of water brake systems had been designed and tested prior to the construction of the SNORT system. The final proof remained, however, with an actual firing. This vehicle was designed expressly to test the water brake. While the ordnance crew readies the sled for firing, the test conductor and his assistant in the fire control center carefully check all circuits, making certain that every data recording instrument is functioning properly. Meanwhile, the camera operators stationed at strategic points along the track, well away from the hazardous area, make last-minute adjustments.
Stand by for a 30-second warning. Mark, 30 seconds. 20. 15. 10. 9, 8, 7, 6, 5, 4, 3, 2, 1. Mark.
You have seen only a few of the design and construction problems surmounted by the builders of SNORT. Probably the world's largest precision instrument, a new tool designed to help guarantee our nation's safety.
What is that?
Lark Hill was the site of, and is named for, the old Lark Ramp, a 450-foot launch ramp that was one of the earliest guided missile T&E facilities at China Lake. Lark was an early Navy program to develop a ship-launched anti-aircraft missile. The Bureau of Aeronautics brought the project to the brand-new China Lake ranges in 1946 so that the test vehicles could be recovered. They fired them on the early tracks, too. The project didn't last long, but it did draw some pretty high-level visitors, along with Fleet Admiral Nimitz. It also proved the utility of tracked ramp launchers, leading to the creation of the 6-degree ramp at G range. Very little of it remains either. The Lark Ramp was a prominent enough feature to leave its name on numerous station maps. Lark Hill, which now hosts a frequency monitoring station and a parking lot, overlooks Lark Seep, the site of numerous environmental annoyances to range operations.
The SNORT track is one of the major test facilities at the Naval Ordnance Test Station, China Lake, California. It bridges the gap between wind tunnel and free flight testing. The most prominent building at SNORT is the headquarters and fire control building. Above it rise the telemetering and communication antennas. Available to the engineers and scientists conducting sled tests are buildings for the assembly and repair of test sleds, facilities for handling explosive ordnance items, and also equipment for the fabrication of sleds. About 1,500 feet from the headquarters building lies the heavily armored blockhouse. It is 200 feet from the track's breach. On the bed of reinforced concrete lies the track of standard railroad gauge 171-pound crane rail, 4 1/10 miles long. Items tested on the SNORT track are mounted on either monorail or dual rail sleds which ride on metal shoes. They are stopped on the track by a water break that makes possible the recovery of valuable sleds and test items. The water serves as a braking agent on the scoop attached to the undercarriage of the sled. The water is pumped into the trough from a reservoir. The terminal ballistics track, more commonly called G4, is located about 16 miles north of the SNORT track. 3,000 feet long, about 1/7 the length of SNORT, terminal and free flight ballistic tests are run on this track. The track is continuously welded 33-inch gauge 171-pound crane rail anchored to the reinforced concrete. The muzzle area of the track overlooks a dry lake bed 500 feet below. Targets for terminal ballistic studies are mounted on the flat land area at the end of the track. Immediately below the track's muzzle is the instrumentation barricade, where most of the terminal ballistic test data are recorded. The B4 track, 5 miles west of SNORT, is the forerunner of the present SNORT track. It was the first rocket sled test track in the country and is still used for general purpose testing. About 2/3 the length of SNORT, B4 is 14,500 feet long. It is constructed much like a railroad track and uses a sand brake for stopping the sleds. The B-58 seat ejection system was tested with the front 40 feet of a B-58 prototype. At that time, this was the heaviest and largest sled ever fired on any track. The sled has 3 cockpits, only 2 of which, the first and the second, are programmed for ejection on this run. The men riding in the sled are anthropomorphic dummies, fully equipped with pilot's gear. The sled, fully loaded, weighs 16,000 pounds. The rocket motors on the sled itself produce a total thrust of 99,000 pounds. The rocket motors on the pusher are 4 Nike boosters. Each imparts 57,000 pounds thrust. When the pusher motors burn out, the motors on the sled are fired, leaving the pusher behind and thus eliminating excess weight. The motors on the sled are fired at intervals to sustain the sled's velocity as the dummies are ejected. Noticeably, this is slow motion coverage. The sled's velocity is 420 miles per hour. Here is the natural speed, and a candid shot from inside the cockpit, which shows a defective canopy lining smash the pilot's faceplate. The lining was redesigned as a result of the information furnished by this coverage. The cockpit section of the Grumman F-9 F-8 trainer was used in a series of tests to evaluate the Martin-Baker seat ejection system. The same sled was used in the series of 7 tests. Some of the runs were at low speeds to simulate takeoff and landing, and others were at high speeds to simulate ejection during actual flight. Mounting the cockpit section on the sled in a 6-degree rotated position simulated an aircraft yaw condition. Part of the test was to see if the canopy would shear off and hit either of the dummies. The ejections were successful. The nose of this Martin Seamaster is pitched up to simulate ditching during takeoff or when crash landing in water. The 3 dummies are ejected by a rocket catapult. The rocket catapult imparts a sustained acceleration to boost the dummies to a height sufficient for the chutes to open before the dummies reach the ground. As a result of these tests, design changes were made to stabilize the trajectory of the seat and dummy. This run at 720 miles per hour and with the same sled and ejection system further demonstrated the need for design changes that would eliminate violent spinning affecting the dummy's trajectory after ejection. An improved drogue chute was later used to stabilize the dummy's trajectory and assure a clean chute opening. The T-2J is North American Aircraft Company's 2-place Navy trainer. A secondary purpose of the SNORT tests was to determine whether the rocket blast of the first ejection would burn the second dummy, which remained in the cockpit. The primary purpose, however, was to prove out the automatic seat dummy separation and chute opening operation. A 4/10 scale model of Convair's F-102 aircraft was equipped with 4/10 scale Falcon missiles. The purpose was to establish the compatibility of the F-102 and Falcon. The missiles were launched under subsonic and supersonic velocity conditions. What looks like explosions along the track are the missile's impact on the sand. Bow and CZR camera coverage furnished detailed trajectory information. This film's exposure time was 40 microseconds. Photographed from every angle as it streaks down the track, the supersonic sled scoops into the water break trough, slowly ending its run. These tests demonstrated the Falcon's trajectory was not hazardous for the F-102, thus proving their compatibility. This sled run was performed to test out the Sidewinder launcher. The standard Sidewinder rail launcher and pylon were installed on the sled, from which the dummy missile was launched. The missile showed no tendency to pitch back into what would be the path of the firing aircraft. Surrounded by the sled's rocket motors, the 275-inch rocket was launched at a high angle of yaw to gather ballistic information about this high-angle launching condition. The data included dispersion, pitch, yaw, roll, spin rate, and actual trajectory. This This run shows the rocket leaving in the upper left of the screen. The runs in this series range from subsonic to supersonic speeds. The Titan missile's inertial guidance components were placed in the nose of this sled and fired down the track. It was possible in this way to compare their performance with realistic velocity and acceleration requirements. The motor is a liquid fuel rocket. It permits controlled, continued acceleration at a minimal G rate. This particular motor can impart 35,000 pounds of thrust for a maximum of 14 seconds. The sled's velocity in this series of tests varied from 400 to 950 miles per hour. Notice how the scoop on the bottom of the sled plows into the water brake, gradually slowing the sled to a halt. As the sled travels down the trough, the water level on the scoop rises and thus gradually increases the braking force. Among the most interesting runs on the SNORT track are those testing the strength and stability of aircraft structures. This B-29 stabilizer was subjected to the shock wave produced by up to 10,000 pounds of TNT. Pressure pickups at the event point measured the intensity of the shock wave. The information recorded in these tests is compared to static test data. In this high-speed photography, shot at 3,000 frames per second, notice the shock wave wipe left to right across the screen. This action occurred in less than 1 second. The stabilizer was mounted on a pylon to avoid possible ground effects. In this series of tests, the speed of each run was increased until the stabilizer's destruct velocity was established. Slow motion coverage taken by a 16mm Eastman high-speed camera more clearly displays the flutter. The maximum flutter before destruction was as high as 25 cycles per second. The FastX camera on the rear of the sled gives a more dramatic view. The markers on the left are 100 feet apart. The black objects coming toward the camera are rivets popping off the stabilizer. Extensively instrumented with strain gauges and accelerometers, the stabilizer was boosted to the critical flutter velocity. The flutter frequency in this case was about 22 cycles per second. Notice the molten metal flashing off the sled's shoes. A FastX camera mounted on the sled behind the stabilizer shows the gradual increase in flutter. On the left are the telemetering antennas. Flying debris broke the protective cover on the camera's lens. An actual model of the A-4D2 aircraft was fired down the track to measure its aerodynamic tail flutter. 6 standard aircraft JATO bottles were attached to each side of the fuselage. These rockets served as pushers. Controlled flutter inducement made it possible to obtain aerodynamic stress and strain data without having to run the sled beyond the structure's destruction point. Such dynamic, controlled, and fully instrumented testing of aircraft structures, ejection systems, guided missile components, and entire weapon systems illustrates the Supersonic Track Division's contribution to this country's research and development programs.
was that?
Deke Parsons was one of those most responsible for the creation of the so-called China Lake Way. Although he was never stationed at China Lake, his collaboration with L.T.E. Thompson, the station's first technical director, helped set the course for developing the entire Navy laboratory system during and following World War II. And although the Navy's role has been minimalized by the Air Force, as usual, Parsons was one of the principals of the Manhattan Project, associate director, ordnance chief, the original weaponeer. And it was Parsons and his Navy cohort, Dick Ashworth, who flew with and released the secret weapons dropped on Japan to put an end to the war. A decade later, by the way, Ashworth would be Knott's commander. Deke Parsons was a very modest man of great intellect and amazing vision, the archetype of the scientist in uniform. And he should be better known to more people.
Omaha to Sacramento. Thousands of miles of steel rail. Across the plains, over the Sierra to the Pacific. A week's journey to new horizons. A 100 years later, at the Naval Weapons Center, China Lake. A supersonic naval ordnance research track, SNORT. 4 miles of heavy steel track. Also, a railroad to new horizons. New horizons in the dynamic testing of advanced military hardware. On the trip west, mileposts clicked past at about 30 per hour. Each mile held new surprises. At the SNORT track, the mileposts go by a little more quickly. 5 times the speed of sound is not unrealistic for these rocket sleds and the tests they carry. Each mile holds new surprises. Data about system and component performance under dynamic conditions which cannot be duplicated in conventional laboratories. SNORT is more than rails and concrete. It's an outdoor laboratory with full instrumentation to record the precise data most useful in furnishing the fleet with weapons that work. Most SNORT tests are documented photographically, often with special high-speed cameras. Impact cameras can capture the penetration of a warhead, and warhead detonation. Cameras mounted on the sled show components reacting to the stress of acceleration and air pressure. Motion picture cameras document instrumented anatomical dummies in ejection seat tests, shown first in real time and at 2,000 frames per second. A rain field can dump up to 9 inches of rain per hour to test the components at operational speeds. An interior camera films raindrops hitting the nose of an optically guided missile. As cameras roll, other sensors monitor the test electronically. Plotters, chart recorders, data tape and videotape can record dozens of channels telemetered from the sled. Data to advance the horizons of military hardware. Like the instrumentation package, the hardware for each test is specifically assembled to meet the test objectives. Machinists familiar with test needs work in SNORT's completely equipped machine shop. Expertise and ability save the project time and money. Engineers working with the machinists can design and build any special hardware needed for the test. On the track, all SNORT tests ride on metal wraparound shoes. The shoe guides and supports the sled, while the bottom lips hold the sled on the track. Small terminal tests like warheads and bombs ride a single rail to a safe, repeatable, and low-cost impact off the end of the track. Large reusable sleds ride both rails. After the test, a scoop beneath the sled pushes against water running between the rails, stopping the sled. These large sleds with their complex telemetry packages are recovered and reused. SNORT tests are powered by solid propellant rocket motors. Motors are selected and pusher sleds arranged to offer the exact acceleration and velocity needed to test the hardware. Since testing began in 1953, SNORT has had many unusual and spectacular tests. A Titan 3C second-stage rocket motor weighing about 100,000 pounds was impact tested for NASA to determine its susceptibility to the shock it would receive if it failed to ignite and fell 2 miles to Earth. In the early 1960s, SNORT helped America's space effort by successfully testing the low-altitude safety ejection system on the Gemini space capsule. Project Catshell remains one of SNORT's most interesting tests. Two 155mm cannons simultaneously fired inert rounds toward the rear of the moving sled, the shell catcher. A 6-ton sled, moving at 1 1/2 times the speed of sound, caught the round softly in a bed of fiber sheets and brought them gently to a halt. The effects of pressure, barrel rifling, and acceleration could be analyzed. Tests of life-saving safety ejection systems continue to be a major area of fleet support. The SNORT facility tests ejection systems at 0 velocity, and at operational velocities up to 600 knots. In this test, the cockpit was mounted in a nose-down attitude to simulate a predicted escape scenario. Tests of another jet show the cockpit nose down and rotated, again to simulate an escape scenario. One of the SNORT tests several years ago yielded some surprising results. A defective tie-down strut ejected the entire cockpit. The anthropomorphic dummy eventually ejected too. 225-foot towers, built for fuse testing, were used to test a vertical seeking ejection seat in a technology demonstration. Ejected in any direction, the seat corrects to vertical, giving the pilot the altitude he needs to survive. Prototype air-launched missiles, not yet certified for air release, can take advantage of SNORT's high velocity and predictability. SNORT is often used to test missile fusing systems and missile guidance and control systems. Systems like this Sidewinder 9L need realistic targets. Here an F-8 running an afterburner.
7, 6, 5, 4, 3, 2, 1, fire.
As the seeker advances, data arrives at fire control from the sled, now moving at Mach 2. Some tests are run at night to eliminate the effect heat waves have on the seeker. Seeker output, control commands, torque, and response time are all calculated from the raw data. Essential information needed before the missile is subjected to the rigors and expense of an air launch. Airframes suspended between SNORT's 225-foot towers are targets for tests of missile fusing systems. Most of these proximity fuse tests are non-destructive. With rapid data assessment and quick hardware turnaround, several tests are run each day. Target separation, attitude, and number were varied during the series to help engineers establish fusing parameters. SNORT uses other specialized targets for specific tests. Concrete and earth simulate hardened land targets for penetration warheads. Steel plates simulate ships and armored targets. Various angles reflect different attack problems. Materials are also tested on the SNORT track. Drogue chutes to slow aircraft after landing were tested for the Naval Surface Weapons Center. Different designs of different materials were released at different velocities. Tests which would be nearly impossible to conduct in a conventional laboratory. Not all SNORT tests are directly defense-related. These shipping containers, loaded with simulated cargo, were launched into a solid wall. The reason? To simulate the jolt air cargo would receive in an airplane crash. The resulting data was used to design new shipping containers and to help change aircraft cargo loading. Though SNORT is NWC's longest and most heavily used track, some special tests are run on the G4 terminal ballistics track. G4, a 3,000-foot-long dual-rail track, features a muzzle which overlooks a 500-foot deep valley. Weapons like this fuel-air explosive, FAE, were tested in simulated air launch conditions. The predictability of track testing was well suited to these FAE cloud dispersion studies. Cameras record the detonation from every useful angle. G4 extends its versatility as a backup track for SNORT. Again, targets reflect test needs. Whether on G4 or the big track, SNORT rail tests are dynamic, fully instrumented, predictable, and reliable. To the military and to the research and development community at large, NWC's high-speed test tracks are indeed railways to new horizons.